So as you can see, it's really hard to draw these squares that are not perfect squares, that don't have these whole number side lengths. Okay, so it's hard to draw exactly 55 squares here. It's hard to draw exactly 18 squares here. But it is possible. Okay, so we're going to try that. So we can draw squares that don't have whole number side lengths. And it's possible because if we take a look at this square here, if I just draw it at 45 degrees along the grid here, we can see clearly that there are going to be, if I count them, I can see exactly 8 squares in here, right? Because I can draw my 4 squares here. There's 2 half squares, so that's 1 full square here. There's 1 full square here, 1 full square here. So there's 8 full squares in here, exactly, not just approximately, there's exactly 8 full squares here. So what that means is, if my area is 8 squares, then the side length must be the square root of 8. And in this case, since there's exactly 8 squares here, this length here is exactly the square root of 8. And on our calculator, our decimal value for this, okay, and this decimal value is not exact, but it's approximately, I'm going to write this approximately, it's approximately 2.8. I'm going to round 2.8, so I'm going to round that to 8.3. So this side length is about 2.83, but it is exactly square root 8. Okay, and this is what we call an exact value. Square root 8 is the side length along that edge. It is a square, and we know there's exactly 8 squares in there, so the side length must be the opposite, or square root of 8. Now, we can draw other squares that don't have whole number sides. And the easiest ones are when we draw this at 45 degrees like this. Okay, we can draw another one that's slightly bigger. Okay, and that, again, that must be a square. And this one's actually easy to count the squares in because we can kind of block this out. There's 8 squares here, 2 here, 2 here, 1, 1, 1, 1. And then there's 0.5, 0.5, 0.5, 0.5. So that if I count that all up, that's 8, 10, 12, 13, 14, 15, 16. Between those two is 17. Between those two is 18. So there's going to be exactly 18 units squared. So the side length here must be square root 18, which is approximately 4.24. So this would be an easy way to draw another square that does not have whole number sides. Okay, so this is going to be about 4.24 or square root 18 in length. And there's lots of these. So this is an easy way to do it, just kind of drawing it at 45 degrees. I'm going to show you another way. And this one's a little bit harder. We're going to I'll go into a little bit more detail how to do this. And it's going to use a diagonal line that's not at 45 degrees like that, but a diagonal line, let's just do a diagonal line like that. Okay? Maybe I'll just extend that a little bit more, and we'll just do a diagonal line like that. So I want to make a 90-degree angle using that as my square side length. And to do that, I want you to notice something, that I've made a right triangle that went 2 up, 1, 2, 3, 4 across. And I'm going to do the same thing. I'm going to make a 90 degree like this. Okay, and you can see probably with your eyes that that is pretty much 90 degrees, but more importantly, how did I get to that point? It's exactly right on the grid line there. And I got that point by just going the opposite. So this is 2. So I'm going to go 2 here, 4 here. So 2 and 4. This was 2 and 4. I just kind of switched it around. And I can do the same thing. Instead of 2 and 4, I'm just going to 4 down. I'm going to go 2 down, 4 across. Okay. And we go 2, 4. And that's going to give me the other corner of the square. And you can visually see that that's clearly 90 degrees. And there's actually a property here that if we switch the vertical and horizontal, we can get 90-degree corners. Okay, so this is a very useful property. In fact, we're going to need to use this property later on when we draw these non-perfect squares. Okay. What might be an easier way to see this is in the triangles that are involved. So if I draw a right triangle here, this right triangle, 2 and 4, this right triangle, 2 and 4, this right triangle on the outside is 2 and 4, and this right triangle on the outside is 2 and 4. In fact, those same triangles actually exist on the inside as well. Okay. But that blue square is definitely a square, and we can actually count up the squares. We've got 4 squares here. This is a 4 by 2 triangle, so 4 times 2 divided by 2 is going to give us 4 here. These triangles are all the same. Okay, so this area inside the blue square has 4 plus 4 plus 4 plus 4 plus 4. So this area is equal to 20 units squared. So the side length here must be the square root of 20. So that side length is square root 20, and that's approximately, when I square root 20 on my calculator, it's approximately 4.47. And if I look at that, yeah, if that's 4, that diagonal line is a little bit longer than 4, 4.5 about, yeah, that seems about right. And that's going to give us this perfect square, oh, sorry, it's not a perfect square, but a square that has an area of exactly 20 squares in it. Okay, it's not approximately, it's exactly 20 squares. So this is a non-perfect square. It's a square, but it's not a whole number side length. And there's many, many more of these. And this is just one way to draw it. So I've shown you kind of 2 different ways we can come up with these non-perfect squares.